Good morning to all. This is Praveen Kumar Saravanan. Today I'm going to take a final presentation for thin film technology paper which I have taken. The topic is fabrication and analysis of thin film gallium arsenide solar cell on flexible thermoplastic substrate using low pressure cold welding. Um, these are all my outline, introduction, experimental procedure, resultant discussion, SEM and photoluminescence spectra, and finally conclusion. Introduction. Substrates have been recently regarded as more feasible flexible substrate than other flexible alternatives due to their low cost and lightweight as well as the high flexibility. If you're seeing that there are a lot of methods they will use, especially in this paper, they used a cold welding method that is also called a low temperature wafer bonding technique that was developed to realize flexible thin film solar cells. And the gold welding method, mechanical pressure, for example, 50 MPa, that means Pascal, which can damage the semiconductor device as well as it reduces the device yield. In this study, we present the fabrication and detailed physical analysis of thin film gallium arsenide solar cell, which is flexible and mechanically stable by the combination of low pressure cold welding method and the epitaxial liftoff. The short form is ELO. The next one is experimental procedure. In figure 1, we can able to see the schematic diagram of fabrication procedure for the flexible thin film gallium arsenide solar cell. Here they used low pressure cold welding technique. So the gallium arsenide solar cell was grown by the molecular beam epitaxy gallium arsenide substrate, and also it's covered by the 15 nanometer thick aluminum arsenide sacrificial layer. So here the gallium arsenide solar cell structure, p-type back surface field layer as well as the p-type base layer are placed at the bottom, and while at the n-type emitter layer and n-type window layer are placed on the top. So the n-type layer and the p-type layer are placed at the bottom and the top of the structure. And the next one is the epitaxially ground gallium arsenide solar cell is formed and on the like the pieces of 0.6 into 0.6 centimeter square, and the ohmic contact layer like the platinum or gold was formed on the top of the gallium arsenide solar cell epitaxy to enable metal-metal bonding with the metallic layer of chromium gold coated on the flexible substrate. So here the carriers substrate like is used in this study was a polyethylene terephthalate, polyethylene terephthalate. The short form is PET film, and a shaft state material it is coated with gold and can be bonded to metallic layers by using cold welding at low pressure. So in this study, the low pressure cold welding process was carried out under the mechanical pressure of 0.4 MPa at 130 degrees Celsius for 10 minutes. So after the low pressure cold welding and the ELO process, the N-type metal grid was formed on the thin film of gallium arsenide solar cell by E-beam evaporation. And the next one is resultant discussion. In the figure 2A, it shows that the SEM image of gold bonding induced by low pressure cold welding, and it is coated on the gallium arsenate substrate after the detachment. So the gold bonding between the chromium or gold metallic layer on the PET film and the platinum or gold metallic layer on the gallium arsenate substrate remained very tight. So after the bonding test, the bonding between the gold surfaces is stronger than the gold chromium PET substrate. So here the bonding strength between the gallium arsenate substrate and the PET film produced by long pressure cold welding was strong enough to hold the thin film gallium arsenate solar cell. So by using this method, a thin film gallium arsenate solar cell was transferred onto the PET film after the chemical etching of aluminum arsenate sacrificial layer. So in this case, we can able to see in the figure 2B. So there is no visible cracking, and the peeled region and defects were found in the thin film gallium arsenate solar cell, which can be like generated carriers. And the next one is like the high resolution X-ray diffraction, like the photoluminescence spectra. And the in the figure 3A, we can able to see the HR XRD curves. The both ground gallium arsenate solar cell and after ELO process. There is a weak regularity of high resolution XRD peaks. So we can able to see figure 3A. The thin film gallium arsenate solar cell is responsible for the invisibly small surface wrinkles, and there is a sharp peak shows slight strained gain P window in gallium arsenate peak. So after the ELO process, the sharp peak will be vanished. So this kind of lift off process we can able to see in the figure 3A. And here the figure 3B, it shows that the photoluminescence spectra of as ground gallium arsenate solar cell and the thin film gallium arsenate solar cell after the ELO process. The active layer as well as the gain P window layer was removed before this measurement. So the PLP position was blue shifted from 831 nanometer to 821 nanometer during the ELO process. And then here the welding temperature is still above the room temperature. So the coefficient of thermal expansion of gold is twice larger than the gallium arsenate. So after cooling down to the room temperature, the gallium arsenate thin film solar cell is strained. And the next one is JV curve of the thin film and external quantum efficiency. So in the figure 4A, it shows the light current density voltage curves of the fabricated thin film gallium arsenate solar cell under one sun illumination. So the thin film gallium arsenate solar cell, here the active area is 36 millimeter squared, and the open circuit voltage is 1.04 voltage, and the short circuit is 17.7 milliampere per centimeter square, and the fill factor is about 71.3 percentage. So overall, the conversion efficiency is about 13.2 percentage. So like it is known as the layer transferred at high temperature. So the drawback due to the high temperature is increases the formation of defects and cracks, which can degrade the solar cell efficiency. So in the figure 4b, it shows the calculated external quantum efficiency spectra of gallium arsenide solar cell. So the difference between the measured EQE in the range about like 650 nanometer. So during this process, topmost gain P window layer, it is exposed to some kind of the dangling bonds, and also sorry. The next one is performance of the flexible thin film gallium arsenide solar cell. So in this case, to analyze the flexibility and the mechanical stability, the fabricated thin film gallium arsenide solar cell, it's shown in the figure 5A. And the performance of the thin film gallium arsenide solar cell, it's same up for the same up to the 2000 cycles continuously. So it shows that the stability and robustness of that material. And then here the weight of the fabricated thin film gallium arsenide solar cell was reduced to 1/27 by replacing the 350 millimeter thick gallium arsenide parent substrate. So here the fabricated solar cell shows some specific power range like 1.501 kilowatt per kg, and the resulting flexible and light-weighted thin film gallium arsenide solar cell has a great potential for its use. And the finally conclusion. So here we reported a new approach for realizing low cost and lightweight and the flexible thin film gallium arsenide solar cell. It is based on low pressure cold welding and the epitaxial liftoff. And the proposed approach is reduced the applied mechanical pressure by 1/155 compared to the method previously they reported in the cold welding bonding. So, and the prevented the mechanical damage is caused to the transferred thin film gallium arsenide solar cell. So this new bonding technique can be used for the fabricating flexible inorganic semiconductor devices on plastic substrates, and can also be used for developing flexible and lightweight gallium arsenide and indium uh, based compound semiconductor device such as light emitting diodes or photodetectors and other electronic and optoelectronic devices. Thank you.